Hey everyone, this is going to be a very short video to go over Hess's law. Normally I have a practice problem at the end of these videos. I do not have one for this one set up, but I want to get the video posted as soon as possible. So probably what I'll do is make a separate practice one for this. So let's jump into it. So Hess's law is the idea that it relies on the idea that enthalpy is what's known as a state function. So enthalpy is a state function, and what do we mean by that? A state function is anything that does not depend on the path. Okay, it does not depend on the path that you use to arrive at it. Okay, on how you arrive at it. Okay, so the example I usually give for this is, imagine driving somewhere you go all the time, like your closest grocery store. Okay, so the overall distance you travel is always the same from your home to the grocery store, but you could take many different paths to get there. So you could drive first to get an ice cream cone and then go to the store. Or you could go buy a cup of coffee and then your ice cream cone and then go to the store. You can take lots of different paths, but the actual distance between your house and the grocery store doesn't change. It's just how you get there has changed. So the distance from your house to the grocery store is a state function. The distance you travel to get there, or the amount of time it takes you, or the amount of gasoline you spend driving there, if you go in a car, those are all not state functions. So those are path dependent. They do depend on how you get there. Enthalpy does not matter how you get there because it is a state function. It's basically a form of potential energy, right? So just like putting a book on a bookshelf, the amount of energy that book has only depends on its height. The amount of energy that can possibly come out of a reaction between methane and oxygen doesn't matter where you got them or how you obtain them. It matters on how much you have of them, but not per mole, right? So the delta H is not going to change based on the path. So what we do is we use that fact and we take any path that we have available to us to calculate the delta H for a reaction. Okay, so the example that I like to use for introducing this is involving the decomposition of hydrogen peroxide. This right here is hydrogen peroxide. We actually used this compound in first semester Gen Chem lab. You decompose it, usually with a little bit of yeast or some manganese oxide, and it bubbles like crazy because you're making this gaseous oxygen. Okay, but we could measure the delta H of that reaction, or we could use some other delta H's we already know. So here we're asked to calculate the delta H of this reaction. Okay, so I'm going to put a question mark there. And we're given these two other reactions involving hydrogen peroxide and water. Okay, so the trick here is this is really just an algebra problem. All right, and if you think of it like an algebra problem, it works out a lot better. All right, so what we want to do is take these two given equations and we want to make them look as much as possible like the reaction that we're trying to get to. So what do I mean by that? Well, in the reaction we're trying to get to, hydrogen peroxide is in the reactants. We're given it as a product, and notice that it needs to have a 2 coefficient, and it only has a 1 coefficient in the reaction we're given. So what we're going to do is we're going to take this first reaction here, we're going to flip it, and we're going to multiply it by 2. So what does that do to that reaction equation? That makes that 2 H2O2 yields 2 H2 gas plus 2 O2. And now, whatever you've done to the reaction, you have to do to the delta H. So you flipped the reaction, so you have to flip the sign of the delta H, all right? And we've doubled the reaction, so we're going to multiply the delta H by 2. Okay, so no, I don't have a calculator, so I'm just going to do this real fast over here. 6, and I'm probably going to screw this up. 376. And that's going to be kilojoules per mole. If I mess up the math here, like, just roll with it. Okay. So, all right. So now On this second reaction, you've got water here, and you have water in the products. So it's a product in both cases, so that's good, but it needs a 2 in front of it. So we're going to multiply this reaction by 2. That's going to give us 2 hydrogens, 1 oxygen, a whole oxygen, right? Because 2 times a half is going to give us 1. And that's going to yield 2 H2Os. And so we've doubled, but not flipped this reaction. So 286 times 2. Boy, it would help if I had my calculator. 572. Okay. All right. So now you have to prove that the reactions actually add up, because that's the point, is that Hess's law says if I can take these 2 reactions and use them to make this reaction that I was trying to get to, if the reactions add up to that reaction, then I can just add the delta H's together, because I've just created a new path to get there. And the path doesn't matter when we're calculating enthalpy because it's a state function. Okay, so notice, and this is notice that you've got 2 hydrogens here and 2 hydrogens here. Well, you've produced 2 hydrogens and then you've immediately used them up, so it's like they were never there. So we're just going to drop those out. Okay. Sometimes we refer to that as canceling, just like you would in an algebra equation, and that's fine. As long as you think about it in an algebra way. Okay, here I've got 1 oxygen and 2 oxygens. So it's like overall I produced 1 oxygen, right? Because I produced 2, but I immediately used one of them up. So we're just going to cancel that one, and we're going to turn this into a 1, okay? Because on net, we've only created 1 oxygen molecule. Nothing else cancels out, so I've got 2 H2O2 yields. I've got 2 waters from here, and then I've got 1 oxygen remaining that I didn't cancel out, and that matches the reaction equation we were asked to generate. Okay, so that checks out, yay. So now we can just add the delta H's together. Okay, so oh, I can't do it that way. So I'm going to do 572 minus 376, and then I'm going to make the signs right. 12, 6, that's going to be 16, isn't it? Minus 7 is 196. Yes, I hope. That seems about right. Okay, so that's going to be negative 196. If you have a calculator at your disposal, you can double check me and see if I'm right. Okay, so what have we done here? Or better yet, what am I queuing on? Like, how did I know to flip and multiply this by 2? Because I'm looking at the things that are unique, right? I've got H2 and O2 in both these reactions. I can't use those to guide how to get to the final reaction. But I've only got H2O2 in one place. That's got to come from here, right? So that's how I knew to look back here and say, oh, I need 2 of those and they need to be on the other side. Oh, water's only here. I need it here. It's in the right place, but I need it multiplied by 2, okay? Then once you get the reactions set up correctly and they add up to the overall reaction that you want, now you know you can just add the delta H's and get the overall delta H, okay? That's a super short introduction to Hess's law. Again, I'll have a practice problem up on this one as well. All right, questions, shoot them to me in the comments. Get in touch. Hope this was helpful, and I will talk to you soon.